Okay, in this video we're going to talk about something called electric potential. But let's start talking off first about potential energy. If we have two charges, I know that these two charges, because they're opposite in sign, have the potential to do work. In other words, the electric field created by these two charges will do work and cause the two charges to move towards each other, right? And so there is a potential energy here. And we know that work is equal to force times distance. And in this case, it's the Coulomb force that's doing work. And the distance and the separation between the charges cancels. And we get an equation for the work, or the energy, of this system, which is K times Q1 times Q2 over R. So this is the potential energy of these two charges, Q1 and Q2, when they're a distance r apart. So obviously as the distance, as the separation between them changes, the amount of energy in this system changes. Okay? And energy, of course, is a scalar quantity, so it doesn't have direction. And it's measured in units of joules. Now, what's more common than potential energy is the electric potential. And the electric potential is the electric energy per unit charge. Okay, so potential equals energy per unit charge. So we're going to take our potential energy, which we just derived, and we're going to divide it by charge. So what we end up with is K times Q over R. And this is our electric potential. And we give it a symbol V for electric potential. So this tells me how much energy another Coulomb of charge would have if I placed it a distance r from a charge. So for example, here is a single charge. And if I put a Coulomb of charge here, which is a distance r away, that charge, that Coulomb of charge there, would have a certain amount of potential. And it would have a different potential if it was here. So let's call this A and this one B. So this is the potential at A when the charge is at A, and the potential at B would be the same amount but at position B. And what we end up with is something called the potential difference between these two. So we could look at the difference between A and B. VA. So VB minus VA. So the potential at B minus the potential at A would tell us the potential difference. And we refer to that as the voltage. So electric potential is measured in units called volts. So the potential difference is the voltage between those 2 points. Okay? If there is a certain potential difference, a certain voltage, then there is a certain difference in energy between those two, and there is the potential for there to be a change in energy or work done by the electric field in that region. Now, usually when we're talking about energy, we're talking about very small amounts of energy. So work in this case would be equal to force times distance, but we also know now that it can be equal to the potential difference times the charge. And again, you can see, go through and see that these two equations are equal to each other. You end up with the same quantity. But the idea here is that we're dealing with very small amounts of energy. And instead of talking about the tiny number of joules of energy, we create what's called a new unit called the electron volt. So 1 electron volt is equal to the energy that an electron gains, so a charge of an electron, gains when it passes through a potential difference of 1 volt. And that works out to be 1.6 times 10 to the negative 19 joules. So 1 electron volt is a very tiny amount of energy, and it's often easier for us to talk about electron volts instead of joules. So the electron volt is a unit of energy which is equal to 1.6 times 10 to the negative 19 joules, and it's the energy gained by that electron as it passes through a potential difference of 1 volt. Okay, so electric potential is a scalar quantity. So what that means is that when you have two different sources of electric potential, so here I have, again, my system of two charges, one positive and one negative. If I chose a certain point P, there will be two different potentials at this point, one due to the positive charge and one due to the negative charge. So the potential here, the total potential, will be the sum of the potential due to the positive charge plus the potential due to the negative charge. Okay? So because it's a scalar quantity, I don't have to draw a vector diagram. I just have to find the magnitude of each of these potentials. So K times Q1 over R1 plus K times Q2 over R2. Now, what's important about potential is that even though it doesn't have direction, because we're not finding direction, we do need to include the sign of the charge. Okay? So this potential here, due to the negative charge, is actually going to be a negative value. Okay? So the sign of the charge in this case is important. That's unlike when we were talking about electric fields and electric forces. Okay, you can have both positive and negative potentials. Okay, so we're still just adding the two quantities, but this case they're scalar quantities, and the sign of the charge has to be included because we can have positive and negative potential.